I take it from far away. So from what is about seismic design, well, traditional seismic design, as we all know, based on force-based approach and the so-called ductility factor theory. What we obtain usually for stability, we obtain stability either increasing strength or ductility, and usually preventing real mechanism by capacity design. We all know how it works when we use different behavior factor, and we usually scale the elastic response spectrum. But what I'm interested in is to see how we allow an active lead state and partially also serviceability or damaged lead state. We permit damage, and at active lead state, usually we say that the structure should maintain potential repairability. That means that we're ready to demolish it because it's potential, it's not repairability. And we know that when we look at high hazard seismic areas like in Turkey, but also in Italy, maybe it's something a little bit more strict, maybe more advantageous after earthquake. Earthquakes for us are reasonably frequent. So what happens if we change our perspective and we think of using anti-seismic devices? I put it in general terms. So this goes for isolation or goes for any other kind of anti-seismic devices. This morning we saw quite a few anti-seismic devices applied to precast structures. Usually the main difference through dissipation, we try to reduce, or isolation to reduce the seismic response. Through isolation, usually what we do, we increase period. If we couple isolation with damping, increased damping means also decreasing the response spectrum, so decrease the input to the structure. The other idea is that we tend to use anti-seismic devices to protect the structure from damage, and the idea is to localize the damage in the devices. And the devices, if possible, should be replaceable. Again, this morning we have seen quite a few of them. The idea is that structure and structural elements should be protected through limited insertory drift demand. Well, I've seen several damages in not very strong earthquake that ended up in building substantially being demolished because all the partition walls were so heavily damaged that repairing the partition walls would have meant also essentially redoing all the electrical wiring, mechanical plants and everything. And the repair would have been essentially more costly than demolishing and reconstructing. So again, I think that limiting inter-story drift demand, it should be a target when we want to effectively design for earthquakes. So how we do it? Either increasing structural period of vibration, this is typical of isolation, increasing the dissipating capacity, this is typical of when you use other type of devices, as we saw this morning, otherwise combining both strategies. What I will talk about would be multi-story precast frame structures. Of course, this is the topic of the conference. So, and in particular, we'll talk about moment-resisting structures. Of course, we can use several types of structural systems, but I will concentrate on moment-resisting. If we look at traditional moment-resisting frames, we end up with pin beam ends and cantilever columns. This is a fairly simple structural system to construct. So it has the advantage of simplicity. Of course, I have no damage in the pins at the end of the beams. The problem is we end up with a lot of damage at the column base. This is not necessarily very effective when we go to the multi-story building, and this is applicable only to 2-3 floors, not much more really. If we look at full frame behavior, on the other hand, we are more able to control drift, to distribute damage to several elements. Usually the strategy is to have weak beams, strong columns, and to try to maximize energy dissipation, trying to control damage. And this is typical when we do, for instance, emulation of casting plate structure. This is typical of casting plate structure. And talking about emulation of casting plate structures, we will see there are several quite common type of structures. But when we talk about connections, we can identify the connection in several ways. This in black is the connection. In the figure in red is the critical zone, and gray is the dissipating zone. These pictures come from FIP 1978, which is most likely known. So we may have connections in several parts. We can have other strong connection up well away from the critical region. And these are two typical types. We can have over strong connections in the critical region with the dissipation happening just outside of that. We saw that this is typical of the Paolo. I was saying this is typical of the Paolo solutions we saw today. Over strong connection and the critical area dissipation occurring outside of the section, just outside of the section. And this is the pin solution. This kind of solution is typical of emulative connection. Usually they are wet connection most of the time. I will try to present today a connection that goes in that position, but it's a dry and replaceable connection. Of course, we can, depending on the type of connection we have, we may have one-way frame with pin-end connection in the other direction, two-way frames. The fully emulative solution is the last one, when we end up having two-way frames and 3D structures. Again, this picture essentially reflects exactly the same thing that we saw before, showing in one single picture several different skin cruciform teeth elements, multiple bay precast elements, all of these usually with connection in the central part, so well away from critical zones. And this is a quick review of what we have in the market, which is very common in the market. This is with inverted T structures. Usually the solution strategies is to have column. On the column is rest of the T-beam with force reinforcement on top, which is ready to receive casting C2 concreting. So after placing the beams, the floor is placed. Usually the floor is placed and propped most of the time. Not always it's possible to have self-supporting slabs, depends on the type of slabs, but eventually the whole thing is cast in situ. This ends up in an emulative structure where all the connections are essentially wet. This is basically the same solution by using the U-shaped beams. So the concreting design includes also the beam, whereas in the previous solution, beams are completely precast. For the rest, it's quite similar. The advantage of this solution is possible to confine the node before casting, and the solution resembles let's say 100% a casting place solution. This is another case. Well, we saw some of this in pictures today, in some photos and so on. This is the case in which the beam crosses the joint, so it's placed and then it's cast together. And again, all of this resemble casting plate structure. The advantage, we know the behavior, we know fairly well the dissipation capacity. We're able to compute the response with traditional means. And beside the part that the structure is mostly precast, it's equivalent to a cast in situ structure with advantages. We know how it behaves, and disadvantages. The design goal is potential repair after a rare seismic event and limited damage after a frequent seismic event. So, overall, it means that if we have a serious earthquake, this structure will undergo very heavy repairs if it is repairable. And this is in the goals, in the design goals. This is essentially the same, so I will not go any further. Different solutions are these hybrid solutions. This can be done with precast or other means. The idea with this kind of solution, this is with two precast rods, press rod, and this is more similar to the press solution. The advantage of this solution with precast, particularly when the pre-stress bars or tendons are not routed, is that damage is concentrated, or better, rotation is concentrated in the joint, and we don't have essentially severe damage, and the pre-stressed tendons or bars have the ability to recenter the system. So the idea is that we end up with very limited drift after the earthquake, very limited damage. It's not always easy to control the drift. To control properly the drift under severe earthquake, it's necessary to tune properly pre-stressing, and the operation is not always that easy as it's said. If we grout, we have the advantage to have an excellent behavior under service or frequent earthquakes, but we end up with more damage anyway with respect to this hybrid solution in case of severe earthquake. And this is essentially the press solution. We saw pictures of this also this morning. So I think that the behavior of this is very clear. What I'm presenting now is a dry-dissipating beam column connection, which was developed in Bergamo by my team together with in the industry making connections to the Atlantic. And the idea, likewise what we saw in the last presentation, is to decouple the bending behavior and the shear behavior. So we have a system to support shear, and then we have a system which essentially works in tension and compression to allow for bending control. The idea is that this bending control system can be activated in any time during construction. So I could place the beam, and of course by its own weight it deforms, and so we have an initial rotation of the joint. And this is, it means that this system has to have quite a large tolerance, because otherwise it cannot be easily activated. Then we can decide to place the form, the topping, and whatever, and then activate the bending control system, or we can activate it after we just place the beam. It depends on what the target is, because of course The earlier we activate the bending control system, the more hyperstatic is the structure from the beginning. Drift are reduced, but on the other side, we might end up with more damage in the joint at the end, or we might need to have a stronger bending control system. So it's a free design parameter, as a matter of fact. Well, we've been working and doing the test in view of CE marking with the N15129. So we had to respect all a series of parameters. The more stringent one are K2, which is the stiffness after yield, the effective stiffness at displacement at the target displacement amount, and the effective dissipation capacity of the system. Since we developed a steel element, temperature is not an issue. Otherwise, that would be an issue. And what we developed is this strange shaped element, but the idea is to have a very well diffused damage in the elements and to have essentially a perfectly symmetrical behavior in tension and compression in the single element. And that's not easy. When you look at the assembled part, this of course allows the tolerances, so it permits to place it correctly. And you can place as many as you want, 2, 3, 4, 5 of these elements, one beside the other, to obtain the performance required in bending. And this is how it looks in the final version. All of these parts are inserts are inserted directly in the precast element prefabrication plant. This element can go in and out, so allows the tolerances to take care of shear forces and to create bend. So this is the EN 1529 requires both test at the displacement level and an overload test at 1.5 the displacement level. This is the final result without at the overstress cycle, and you can see this is the plasticized area, so what goes beyond yield, and it's quite evident that it's very uniform. And these are the plastic strain. So this allows to dissipate a great amount of energy and to limit damage in the elements. In fact, maximum deformations in this element arrive at 4 or 5%. And this is the theoretical behavior we obtain. This is the cycles up to 5 millimeter, which is the target displacement. And this is the overload cycle up to 8 millimeter. And you see that the behavior is extremely stable. And this ensures and highly dissipative. I mean, this is an almost ideal plastic cycle, which was the target we were placing. We really didn't want much pinching or other things in the cycles because it tends to be difficult to control, particularly if quality of steel is not particularly stable, and that happens the case. So this is the device in the testing machine. This is after overload, the only damage. This is very little fracture, which is within acceptable limits. And that's the only damage that can be observed. We did a lot of shape optimizations. We see only the 3 last cycles here superimposed. We went through a lot of tests, first numerically, and then when we started to experiment, of course, numbers always seem to show that things work perfectly. Then you go to the testing machine and problems come up. Because there are phenomena that we are not able to really simulate correctly, even with the best mental improvement you can think of. And this is the experimental behavior up to the displacement, design displacement, and the overload cycle. The overload cycle is not very clear. This is tolerances. Of course, the tolerance is in the pin. So we've been working with that also to reduce that slip. But that slip is quite normal when you work with pins. It's not really an issue, but has been mitigated in the latest version. What I'm showing now is a numerical example. We have a frame here with pin connection. The frame is 8 meter, is in two directions, 8 meter in each direction, the column span. We stretched the span. We stretched the span so that it would be meaningful for precast structures. And also the loads are quite high, 10 kilonewton per square meter, the permanent load, and the live load 4 kilonewton per square meter. So we wanted to see when we bring the system at the limits. And this is with pin and connection, and this is with the device we developed. We did an analysis with Midas and the history analysis. The columns are different, 700 by 700 in the pin and the beams, 600 by 600 in the frame solution. And well, this is the constitutive relation used for the analysis. If we go to the result, when we ran an analysis with an artificial accelerogram, we know that we use, instead of a set of natural scale accelerogram, we use an artificial. Usually this is more severe. This is not realistic. But nonetheless, what is interesting is to see the response. I will concentrate on the energy dissipated. As the serviceability state, the capacity, the dissipation of the system with dissipating devices is 1.5 times higher. And it's more interesting, the dissipation of the columns is very little. That means that in the solution with pin and beams, we will have damage in the columns, whereas in the other case, we have little or no damage. If we look at the life safety ultimate state, again, the capacity of the system to dissipate energy is much higher, almost twice. And again, the column is much less damaged. So this proves that the residual displacement might appear higher, but again, these devices, this is the highest residual displacement at the most stress floor, which is the top one. And this can be easily substituted, so it's not an issue. And if the column remains essentially elastic, once you remove or release the devices, the system has the ability to recenter mostly. And this is shown, this is the dissipation in the columns. Orange is the one with dissipating devices, blue is the one without. And this is the dissipation, is the most stressed device over there. And it is quite evident that these elements provide the capacity or the ability to dissipate a large amount of energy. Conclusions. So, we presented a dissipating beam column connection. The adoption of these type of connections allows to concentrate the damage in the connection in elements which are easily replaceable after the devices meet the N1529 for CE marking, and it's possible to control the interstory drift, preserve structural element, concentrate damage in highly dissipative elements. Now we are an experimental campaign is undergoing full-scale tests, and we see if all I said is true. Okay, thank you very much.